All right, so here's just a quick review of kinematics: displacement, velocity, acceleration. So here's my example here. Let's say got a little person here. Let's say they walk from here to here, and say 6 meters. 6 meters. Okay, so they go this way 6, and they come back this way 6. So we say, what's the displacement? What does displacement represent? Well, here, displacement is just how far you are from the starting position. So if this person goes 6 meters that way, and then 6 meters back, their displacement is 0, because it's how far they are from the starting position. Well, they're back where they started, so displacement is 0. Don't get that confused with distance. Distance would be the total amount moved. So distance would be, here would be 12 meters, because they went 6 meters this way and 6 meters back. And then now velocity. Velocity is just the, velocity would just be the rate of change of displacement, or the directional speed. Let's say it took this person 12 seconds to move all 12 meters. So they'll say, oh, 12 meters in 12 seconds. That means the velocity here is 1 meter per second. What that means is it's the change in distance over change in time, the rate of change of displacement. Okay, now so here we have acceleration. Acceleration would be the rate of change of velocity. So let's see, let me give you an example of what that means. So here we said that our rate of change here was 1 meters per second. Well, that's for the entire time this person traveled, which means the velocity did not change. So in this example, our acceleration would be 0. Nothing was changed. But let's say that, between the, let's say, 4th meter and the 6th meter, their velocity was 0.5 meters per second. And then when they went back from the 6th meter to the 8th meter, the velocity was 1.5 meters per second. All right, so what that means is this way, velocity was slowing down, so acceleration is negative. And this way, velocity was speeding up, so acceleration is positive. So it's just an example of what happens when we have change in velocity over change in time. Acceleration is the rate of change of velocity, which means change in velocity over change in time. All right, so now it's time for big kid stuff. This is the calculus. So I have a velocity equation here. I know it's velocity because it's the V for velocity. That's how we know it's velocity. Okay, so we'll say, remember, we have displacement, velocity, and acceleration. We said that velocity is just the rate of change of displacement. So it'll be, I had like change D like that. Well, so we don't get confused, I'm going to use S here instead. S for displacement. So I can rewrite it like this: ds over dt. Oh, what does that look like? Oh, that looks like a derivative. Derivative, yes, a derivative. So then the rate of change of velocity, over change in time is just, dv dt. Oh, that's just the derivative of velocity is going to give us acceleration. And then what if I want to go backwards? If I have acceleration this way, antiderivative or integral. If I go this way, velocity to displacement, that's just the antiderivative or the integral. Okay, now so let's look at this equation, this one equation here. Here we go. This should look very familiar. We actually did this in class. Yay. Okay. All right. Let's say I want to find out what the velocity is when time equals 2 seconds. So when t equals 2 seconds. Well, I'll just put 2 in here for t in here. That's just regular algebra. Remember, that's so hard. So v2 equals, remember, that's just notation. When t equals 2, I want the velocity. So 2 here minus 0.32 cubed plus 2. And that's going to give me 3.6. So my velocity is 3.6 when, at 2 seconds, it's 3.6. Well, what about with the acceleration? What's the acceleration when time is 2? Well, what I need to do is I need to find the derivative. All right, well, what's the derivative of velocity here? Well, we want this. So, okay, well, power rule. That's just going to be 2. Remember that? Oh, power rule. That's going to be minus 0.9 t squared. Power rule. Oh, wait. This is t to the 0. Oh, put a 0 there. Now it's 0. So I can leave that there. So this is my derivative. Okay. Well, now I can find the acceleration at 2. So 2 minus 0.9, 2 squared. And that's going to give me, negative 1.6. Oh, negative acceleration. What that means is we slowed down when t is 2. Well, let's say I wanted to find the distance. The distance traveled from 0 seconds to 2 seconds. Well, distance comes from the displacement. So, I'm going from velocity to displacement. I'm going backwards. So it's going to be an antiderivative or integral. Well, okay, integral. So integrate our formula. So then it's 2t minus 0.3t cubed plus 2 dt, because this is in terms of t. Well, you might be thinking, Mister, this is an indefinite integral. I'm going to have a plus c. I'm kind of confused. Well, it's not indefinite because we're given our constraints here between 0 and 2 seconds. So, 0 and 2, like that. Remember, displacement is just how far you are from your starting position. I want everything. I want the entire thing. Because remember, in our example, person went here from 0 to 6, like this, and then back. So the displacement was 0. But in this, I care about the entire distance traveled from here back. So this way, displacement was positive. This way, it was negative. But you know what? We're going to make the entire thing positive so we can find the distance traveled. We do that by absolute valuing this here. And all you'll do is type this in the calculator just like this with absolute value symbols across your equation. And if you do that, your answer should be 6.8 meters. Happy face. All right, now look at what we have here. This is a velocity graph. And I know it's a velocity graph because there's a big V right here, velocity. All right, so let's look at a question you could probably be asked when given this. Very first thing they'll say, hey, when is the particle that this graph represents, when is the particle first at rest? Remember, you're at rest when velocity equals 0. That means you're not moving. If this is the velocity graph, I want to know where the velocity equals 0. No. Because as you can clearly see, these are your values here and here and here for those. Velocity not 0 there. Velocity is 0. We know when the graph of velocity crosses the x-axis right here and right here. These are the two places where velocity is 0. Clearly says this is a velocity graph. Velocity 0 here and here. So at those two places is when the particle's at rest, when velocity is 0. Okay, so one more thing you can say here is because I have my velocity equaling 0 here and here at these points, those 2 points there and there, that is actually where the particle will change directions, because you change directions after your velocity can come to a stop. It's like, well, if I'm moving somewhere, I can't change directions until I stop. So it changes directions twice, here and here. And you change directions because down here the velocity is negative, because see, negative values. Down here the velocity is negative, so that means you're going backwards. But then, now velocity is positive here. Now you're going forward. So you're going forward here. Velocity is still positive. Then all of a sudden velocity changes again. Now it's negative, so you're going backwards again. So that's how you know at the zeros here is where the velocity will change directions from negative to positive, positive to negative, just like that. Great. Now, what if I say, find when the acceleration is 0. So when is the acceleration 0? Remember, acceleration is the derivative of velocity, dv dt. So that is going to be when the derivative equals 0, or when the rate of change of velocity is 0. The slope equals 0. Oh, look at that. That's right here. Oh, look at that. That's right here. Look at that. That's right here. Whoop, right there and right there. So these are all points where velocity is going to, where acceleration is going to equal 0, when the rate of change is 0. And we know the rate of change is 0 because, look, we have maximum and minimums here, maximums and minimums here. Like we said before, the distance would have to be represented by the integral of velocity. Remember, an integration represents the area under the curve. So if I said, let's say between 0 and 3 seconds, show me what that would look like on this graph. The distance, well, or the displacement, be from here to here for between 1 and 3 seconds, like this. This would represent the displacement or distance. Well, what I just colored in, technically that's the displacement. If I wanted it to be distance, this needs to be made positive. Since this is under the x-axis, this area is negative. This one's positive because it's above the x-axis. If I wanted the actual total distance, I'd have to absolute value everything. So then this would have to be positive, absolute value that, add those two together, and that'd be my total distance. Without doing that, it'll just be displacement. That's why if I wanted the distance, I absolute value that, just like that. Displacement would just be, this is an S for displacement. Displacement would just be this.